This is Alix Paultre for EE Times, and I'm here at the VACUUMSCHMELZE booth with Michael Weickhmann. He's their Director of Applications Engineering for Permanent Magnets. How's it going, Michael?
Very fine, thank you very much. We are here and we've made up a booth for the people who are very interested in high-performance machines and high-performance technology, especially on the basis of magnetic material. That is, on one hand, the soft magnetic material based on nickel iron, cobalt iron, and on the other hand, the permanent magnets based on sintered neodymium iron boron and samarium cobalt.
Now, Mike, VACUUMSCHMELZE has been doing this for quite a while, haven't they?
Well, we have actually accomplished more than 90 years of the anniversary, and our company has a size of 4,500 employees, and we have a annual turnover of roughly 400 million euros.
Wow, so you've got a lot of attention here at the booth, I imagine.
Yes, especially with this kind of aircraft that we have here. This is an aircraft that is propelled purely electric. It's an acrobatic aircraft which has an electric engine of 220 kilowatts of power, which means it's comparable to a combustion engine of a 7-liter Lycoming, which has a weight, if you look at a combustion engine, of 220 kilos or something. And the electric machine only weighs something like 45 kilos, so we have a power density of roughly 5 kilowatts per kilogram, whereas the combustion engine has a power density of 1 kilowatt per kilogram.
Now, obviously it's not just because you threw in any old motor. There's a lot of very, very sophisticated technology inside of these motor components, because you don't actually make the motors, you make the components for the motors, correct?
Exactly, and the performance lies in the quality of the material. We are talking about, for example, a cobalt iron laminated stack for the stator, which is laminated on thicknesses of 50 microns. 50 microns, that's a very thin layer, and it has a packaging density of roughly 98%. So we are actually producing these stator packages to reduce the eddy current losses and to increase the efficiency of the motor. That is one issue that we're very much concentrated on, is our grades, our alloys that we're working with. And on the other hand, we have magnetic material based on samarium cobalt for this engine, which is at the moment the highest remanence at a high temperature of something around 150 degrees centigrade. It is well above 1 Tesla of remanence.
Well, you know, and that's very important when you start thinking about these energy densities, you start thinking about the power, the torque that you can get, because beyond electric aircraft, we've got electric trucks, electric vehicles. I mean, the entire application space of electric mobility, just better motors, right?
Sure, but there we have to really look at the market, and we are, as far as the high performance technology is concerned, like the Formula student cars, the racing cars, we produce machines which have a very high density, whereas the normal machines that are incorporated in hybrid cars for the normal consumers, they're usually based on silicon iron, which is a standard electric steel. It's not the cobalt iron or the nickel iron that we're using.
True, but I mean, yes, granted it's a more expensive solution, but if I can increase my efficiency that much, I can shrink my battery.
Exactly, and that is one of these issues that we're talking about, especially with this aircraft. We need a very light aircraft with a very high performance. The torque needs to be there the moment he switches on the engine, the moment he does the loop. He needs this kind of power, and that is why we say this is our future. We can show the limit. We always say shifting the limits or think the unthinkable. That's one of our mottos.
Well, VACUUMSCHMELZE was also involved in that solar craft that flew around the world using solar power.
Exactly. There we used a different grade, a nickel iron grade for the laminated stack for the motor, and neodymium iron boron magnets. But these motors were designed especially to reach up to 97% of efficiency, which means only 3% were in the losses, and that reduced the weight of the battery, as you said before.
One of the things I like talking about, because of this very issue, everyone keeps focusing on the battery when it comes to vehicles. Aircraft, cars, regardless, they focus on the battery, when in reality, if you improve the electronics, you can shrink the battery or not even worry about the battery.
Yes, this is actually the case, and this is what we have done with the solar impulse as an example. But of course, we need high performance in these engines. We need the high performance in these acrobatic aircrafts, because the moment they switch on the motor, the moment they really are turning on the propeller, they need the maximum torque, and that is something that an electric machine, a permanent electric machine, is actually able to deliver.
Well, you know, and on a side note, I'm guessing that the acrobatic maneuvers are actually going to be better because he has all that torque right there.
On the top, on the switch on, he has this kind of power. And of course, at the moment, we are not yet in the air. We are still having to approve all the regulations. So it will take a bit of the time, especially for the company called Evolaris, which was a spin-off of the University of Applied Science in Biel in Switzerland. And they still have to do a lot of work in order to get the first flight ongoing, which will probably be in the first quarter of next year.
Well, we'll definitely follow up with you then.
Sure, that would be very exciting. We will definitely attend this kind of flight.
Excellent. So now, Mike, why don't you, before we close out, give me a little bit more about some of the other highlights here at the booth, and then we'll close out and I'll let our audience know where they can go to get more information.
Of course, we have, apart from the soft magnetic and permanent magnetic materials, we also produce inductive components, which are in the controller of a lot of these electric machines, even in cars. And we do a lot of scientific application like undulators, like quadrupoles, hexapoles, octupoles, which are in the accelerators you will find in Grenoble, in CERN, in XFEL, wherever, even in Great Britain, in the Diamond Light Source, or in Korea, in Pal. So we're worldwide active in scientific application as well. So this is a bit of a potpourri that we're dealing with.
Well, but they do have common denominators. An accelerator needs magnetic control, it needs precise, it needs very powerful magnetics.
Exactly, we need powerful, precise angularity, precise magnetic moment, precise resonance, and that is what makes this company so exciting, because we're always working at the limit. And that is, at least for my work as an application engineer, it's always an exciting thing.
Well, you're quite an exciting person, Mike. I really appreciate it. Your passion comes through and I love it. Thank you so much for taking the time at this busy show.
Thank you very much as well. Thank you and have a nice time.
Yeah, thank you, and thanks for taking the time to be with us.